This video is going to help you to add stochasticity to an existing spreadsheet population model. At this point, you should already know what stochasticity is in the context of population models, and you should have a fairly good idea about how to develop a population model in a spreadsheet. We're going to be using a recursive model where you're looking from one time back on a previous time. So let's take a look at what we're working with so far. We're looking at a model that predicts population size at future times. Usually we start off with a relatively small population size, and that's relative to the carrying capacity. So populations can grow and grow and grow, but eventually something limits them. They run out of something. That something could be all sorts of things. It could be territory, it could be food, it could be an increase in disease transmission as we crowd individuals. There are lots of ways that populations can be limited through density-dependent effects. And usually that carrying capacity is identified as a line, as a number of organisms that we can cram into this space. And if we go above it, the population is going to shrink because those organisms aren't each getting enough of whatever it is that they need. So the population will continue to grow until there are enough density-dependent effects to slow it down. What we've learned previously is that there is often environmental stochasticity that results in population sizes, in the maximum population sizes that can be supported by a habitat varying over time. So some years there's going to be a good year, other years there's going to be a bad year. And in a good year, we might be able to support many more individuals than we could in a bad year. So our population model looks a little like this. We're predicting the number of individuals at one step into the future, whatever that step might be. And that's based on the number of individuals in the population, n sub t. So where t is the population time. And in a lot of the ones that I do, we're going from time 0, but sometimes you'll see this as a year or as a generation or something. And then we're adding to that the number in that population multiplied by the intrinsic population growth rate, and then multiplied by a density-dependent term that essentially puts the brakes on the population as they get closer and closer to carrying capacity. So we're going to work with a population that has a few basic parameters. We're going to start our initial population out at 500 individuals. The intrinsic growth rate is 0.5. We're going to give it a minimum carrying capacity of 9,000 individuals and a maximum carrying capacity of 12,000 individuals. All right. So let's switch over. We'll make this a tiny part of our screen, and then we'll focus on the spreadsheet from here. Okay, so you should already know basically how to make a population model. It's not going to work out yet because we haven't given it carrying capacity. So here's our model thus far. B2 is the number of individuals in the population at time 0. And then we're multiplying that by the intrinsic growth rate, which we're storing in cell E2. We're adding money signs so that that always refers back to that same cell regardless of where we copy the formula. We don't have those money signs when we're referencing the population at time 0 because in time 2 we want to use the population from time 1. In time 3 we want to use the population from time 2. Those are relative references, and those are going to follow us around wherever that formula gets copied. So that's multiplied against our number of individuals at time 0. We have our density-dependent term here, and that's what's important. This money E, money 3, refers to the cell below R. We're going to have to change that. And we're going to make that into a relative reference. So instead of referring to E3, Let's go in here and modify it to send it to C3. C3 is the cell right next to our population at time t1, at time t equals 1. All right. So it's still not going to work. Don't worry, we're about to fix that. See? It didn't work. All right, how do we fix that? Well, here's our carrying capacity minimum. Here's our carrying capacity max. Oops, and we'd like that to move over so you can see it. We'll have 9,000 individuals for our minimum, 12,000 for our maximum. And then at each time that we're predicting a population size, we're going to create that instantaneous carrying capacity. So we're going to do rand between, and we're going to give the bottom number, which is always in column E and is always in row 3. And remember that different programs have different delimiters, either a comma or a semicolon. In the program I'm using, it's a semicolon. Yours may be a comma. And then we're always going to refer for our maximum value to column E and row 4. So we're going to have a random number between those two values. And there we go. So in this particular year, we've got a value of 9,458 individuals as our carrying capacity. And we wind up calculating that our population grows to 737 individuals. Let's go ahead and drag this out to our 25 generations. And now we can see the effect of that variable carrying capacity. So I think it would be really helpful if we could add a population, and this one's going to have a static carrying capacity. It's not going to change. So let's take our formula from here. We're going to copy it here. And we're going to have to do a little adjustment to make sure that it's in a place that we can refer to. So we want to make sure that we're not just copying over what's going on in the other population. We want this to be a separate one that has its own carrying capacity. Okay, so our carrying capacity is 10,000. And that's our stable carrying capacity. So let's call that K stable. And we'll put a little equals sign in here to make sure that we know which one's which. Okay, done. Except it doesn't like an equals sign at the beginning. So we'll just leave it at K stable. Fine. All right. So we're going to have to fix up our formula. We're going to make that now refer to the B column, because we want this, as I said, to be its own separate population. And then we're also going to have to fix the reference to the carrying capacity. And we're going to make that an absolute cell reference to G3. And we'll do that one more time. This is not going to work because we don't have an initial population. So let's go ahead and finish our formula. add in our initial population, and see what happens. They're pretty close. Turns out that there's a little bit of difference because we had a smaller carrying capacity, but there's not a ton of difference at small population sizes. One of the things that we do see is we see population fluctuations in our original, our stochastic population, and we don't see that in the other population. That's an interesting dynamic, and it's one that's being pushed just by the stochastic nature of carrying capacity. It's going to get more complicated as we increase the intrinsic growth rate, and that's going to give us some weird dynamics that are going to be a little bit harder to follow, but are also really important in terms of that being exactly what we want to see. So let's go ahead and add a chart. Remember that we don't necessarily want this kind of chart. We're going to want to create a scatter plot. All right. So we'll do XY scatter. I like to choose lines because that's what we usually see in these kinds of plots. We'll finish, and there you can see it. So I'm not going to bother with doing labeling in this one just because you're following along, but really, if you're ever making professional graphics, you should always have labels on the axes, so don't forget that. Let's crank up that R value just a little bit just to see what happens. All right. Let's try 1.2. Not bad. We still have a population that's making its way, that's doing all right. Let's try a little bit higher. Now we see some really interesting dynamics where the population's getting pushed much, much smaller, and we could keep going, and we'll see that the faster the population grows, the weirder some of those dynamics occur. We don't have anything to catch what happens when the population falls below zero. So right here, we would see that the population might have gone extinct. But this kind of shows you how some of those dynamics are going to work out. So I hope you've enjoyed the video. I hope that helps you to incorporate stochasticity into some of your spreadsheet models. And at least as a beginning, there are some more elegant ways that you can do this. There are some things that you can do to make the process cleaner, to catch negative values, that sort of thing. But I think that this is a really great way to get started. Thanks for listening. Have a great day.